This question is about gaseous equilibria. Figure 1 shows the effect of pressure on percentage yield. So we can see that pressure is increasing from the left to the right, and yield is up our y-axis. So we can see that as pressure increases, the yield actually comes down. And we can also see we've got two temperature curves. So as temperature increases, our yield also comes down. And it says, explain how figure 1 shows the forward reaction is exothermic. So as temperature increases, yield decreases. That means that therefore equilibrium shifts left when temperature increases. So the reverse reaction must be endothermic, as shifting in the endo direction opposes the increase in temperature. Conversely, that means the forward reaction must be exo. State whether the forward reaction results in an increase, decrease, or no change in the amount of moles of gas. So if we go back and look, remember that increasing the pressure decreased the yield. So increasing P decreased yield. Now increasing P shifts to side with fewest moles, and if we decrease the yield, therefore fewer moles on left, because we went backwards when we increased the pressure. Okay, and as a result, therefore, there must be more moles on the right, so the forward reaction results in an increase in moles. So there was lower yield at higher pressure. So we can just write down the things that we wrote above when we were thinking it through. Increasing P shifts left or backwards. To side with fewest moles to oppose the increase in P, as fewer moles exert less pressure. Explain why using a catalyst has no effect on percentage yield. Using a catalyst increases the rate of the forward and reverse reactions, and the key thing is that it increases it equally. Hydrogen and nitrogen react to form ammonia. At equilibrium at 745 Kelvin, the equilibrium constant is 0.118 mole minus 2 dm6. At 745 K, 0.15 decimeters cubed of the equilibrium mixture. So this is already equilibrium amounts, giving us the moles of hydrogen and the moles of nitrogen, and it wants us to calculate the moles of ammonia. So let's first of all just write our expression for Kc. So remember, Kc is an equilibrium constant of concentrations. Products in square brackets for concentration. We've got 2 ammonia, so ammonia squared over hydrogen concentration cubed times nitrogen concentration. Now remember, these are concentrations. So our 0.118 is equal to the amount of moles of ammonia, which is the thing that we need to find, divided by the volume, 0.15 squared, divided by the moles of hydrogen, 0.0285 over the volume, cubed, moles of nitrogen, divided by volume. And now what we've got is essentially just a maths problem. So I'm going to first of all multiply 0.118 by 0.0285 over 0.15 cubed, 0.0870, 0.15, and that is going to give me the moles of ammonia divided by 0.15 all squared. So let's put that in the calculator. And we've got 0.087 over 0.15. So 4.69 times 10 to the minus 4. So what I'm going to do now is I'm going to square root that. So then I'm getting moles of ammonia divided by 0.15 equals 0.0216. And then I'm going to times by 0.15 to get rid of that bottom line. And that is going to give me my answer. And I'm going to give it to 3 significant figures. So 3.25 times 10 to the minus 3 moles. Calculate the value at 745 for the dissociation of ammonia. So when we want to go back and we want to look at how this compares to our other equation. So we can see that our original equation, which went 3H2 plus N2 makes 2NH3, had a Kc value of 0.118 moles to the minus 2 dm6. And what we've done here is we've reversed it. So our Kc value is going to be 1 over 0.118. Which if we get on our calculator is coming out to 8.47. And if we do the inverse of the units, we'll get moles squared dm minus 6. It's 1 over those units. We're going to change the sign on the units.